Today we are going to discuss about millimeter wave communication. In this presentation, we are going to see the overview of millimeter wave and the technologies, applications, what are all the challenges we are facing in millimeter wave communication and what are all the future trends. The introduction of millimeter wave. Here the frequency range of millimeter is from 30 GHz to 300 GHz, which is much higher than normal frequency range we are using in ISM, GSM band and MICS band. All these frequencies are around 2.45 or 100 MHz or 108 MHz. But here in millimeter wave communication, we are going to use the frequency range from 30 to 300 GHz, and the key technologies we are using millimeter wave communication is majorly on 5G and 6G communication. In short, we can say next generation communication all are going to use these millimeter wave communications, since the spectrum which is available is already it is congested, or more number of users have been accommodated in the available spectrum. So we are going to move into millimeter wave communication. And the major thing why we are moving into this millimeter wave communication is because it supports multi gigabits data rates, through which we can easily access all the videos without any much more buffer, and the data rates will be higher compared to your normal communication systems. And it enables high capacity wireless links, which means we can accommodate more number of customers in this millimeter wave communication. And here are the need for millimeter wave communications. Since in older days we had only one mobile phones in a home, but nowadays the mobile phones which we are using is has been increased in a large number, and growing the mobile phones has demanded the datas which we are already congested. So we have to introduce some new technologies or new frequency bands to accommodate all the number of users, and the data has to be managed. And also the spectrum scarcity has become a major need for emerging into millimeter wave communication. The spectrum scarcity is below 6 GHz, so we are moving into millimeter wave communication. And high bandwidth availability, we are having a very high bandwidth in millimeter wave communication, so that we can accommodate more number of users, and the capacity is also been increased. And low latency communication is also a major cause why we are moving for this millimeter wave communication. And these are the common spectrums which we are using for millimeter wave communication, and the bands are from 28 GHz, 38 GHz, 60 GHz and 73 GHz. Since this is a large contiguous bandwidth, more number of users can be accommodated at these bandwidth when we are using sub bands. And if we are going to split the frequency bands into reusable channels, then the number of users will obviously increase, and it is mainly suitable for high speed communication. Henceforth we are using this millimeter wave communication for your 6G and next generation communication. So we have to know the spectrum range of this millimeter wave communications. And next, coming to the session propagation characteristics. Before we are using millimeter wave communication, or before we are going to design any antenna for millimeter wave communication, we should know the propagation characteristics of millimeter wave communication. So the characteristics of millimeter wave communications are, they are very short wavelength, and henceforth the frequency is higher, and high free space path loss. That means we can easily obtain line of sight propagation, and the space path loss will also be high. Limited penetration through obstacles. This is a major drawback or shortcomings of this millimeter wave communication, since because the input are going to be short wavelengths, maybe in short pulses, there are more chances of getting reflected back to the transmitter even before reaching the receiver. So this is the major constraint of millimeter wave or terahertz communication. This is the major constraints, and these millimeter wave and terahertz emerging technologies, these are all sensitive to blockages. Means like normal propagation standards, like normal radio wave propagation, they cannot penetrate through obstacles, so they are very sensitive to blockages. We have to find solution for this in future emerging techniques. And coming to the antenna technologies, whenever we are introducing a new spectrum or newer bandwidth for the users, we have to create or we have to design an antenna for that spectrum range. So here for millimeter wave technologies, we have to build an antenna with a miniaturized size in millimeter, or we can go for phased arrays because all the inputs are going to be short wavelength or pulses. So it is better to go on arrays or massive MIMOs. And here one of the important technique is beamforming, because we have to direct all the beams towards the transmitter. So this transmission can be made easier through beamforming. Here we can use adaptive beamforming to manage these problems. And we are going to use compact antenna structures, obviously microstrip patch antennas, which are usually compact structures. Coming to the next session, applications. So we are going to use the millimeter wave communication for 5G, 6G and beyond these new generation applications. Fixed wireless access, here also we'll be using all accessing techniques like multiple access techniques, CDMA. Currently we are using non-orthogonal frequency division multiplexing, NOMA, OFDMA, and all these things are being carried out until 5G or 4G. And here we can easily use NOMA or other access techniques. And we are going to use in autonomous vehicles. Majorly, it is very useful in IoT and smart cities. We can easily able to embed these antennas into smart integrated units, because the millimeter wave antennas are miniatured in size. So we can easily embed these things in your day-to-day life or IoT, and it is very easy to fabricate into your IoT blocks. And then smart satellite communications, we are going to use smart antennas or reconfigurable antennas. Advantages already we have discussed. These millimeter wave communication usually have high data rates, larger bandwidth. Larger bandwidth, we are going to accommodate n number of users which are not being accommodated in the available spectrums. And the high data rate implies there is a no or low buffering for all your uplink and downlink communications. And improved spectrum efficiency, if the number of customers is increased, obviously the efficiency will also be increased. Support for dense network, since even now the mobile phones has been increased, and on the smart cities or future upcoming AI technologies will be having very dense data rates and dense networks. So obviously we have to switch over to the next generation, which can be 6G or millimeter wave or terahertz wave communications. And the challenges we are going to face in this techniques are propagation loss. As we mentioned, the wavelength is very small or in pulses. They are going to create a propagation loss. The transmitter may or may not able to transmit the entire pack of data to the receiver. Some may be missed or some may be reflected. And atmospheric absorption is very low here. Hardware complexity is, if we are upgrading the antennas or any techniques, the hardwares or softwares or cognitive radios, whatever may be, we have to upgrade the device as per the specifications which we are designing the antenna for the upgraded technologies. And beam alignment requirements, it is a major thing which is unavoidable in millimeter wave communication. Beamforming, either adaptive or switched beamforming, has to be employed in order to avoid all the beam spillage and to pull over all the transmitted data to the receiver. We have to align the beam in the required challenges. And in 5G and 6G, we all know enhanced mobile broadband, ultra reliable low latency communication. We are going to move into AI enabled wireless system. Terahertz communication is going to evolve after this stage. So, if we are going to do any research, these are the future research directions. So, as I said, intelligent reflecting surface or reconfigurable antennas, beamforming, energy harvesting, or terahertz wireless systems. Thank you.